So I thought I'd tell you a little bit about graphical user interfaces. If you, just in case you got sick of using command line tools, I want to at least show you the possibility of using graphical user interfaces. And so one thing that I actually use quite often is a graphical user interface to git diff. And so the reason is git diff works fairly well for small changes. So let's say, do you use who does not use git diff? Okay, so git diff, when you type in git diff, it shows you what text you've changed in your repository since you've last committed. Okay, so my normal workflow is I have a repository, I change some files, and then I check with git status which files have been changed. So git status, if you type in git status, it just lists you the files that have been changed. And then I type in git diff to see the line-by-line changes that I've made. And I just double check that all these changes are kind of make sense, so that maybe I've added crazy print statements, so I just want to make sure that I remove them, and then I do a git commit and push. Right? So the git diff is really kind of the last stage of checking that what I've done doesn't mess up things. So the command is just git, as shown up here, git diff. If you type that in, you get something like this, a screenshot below here, and essentially the way you need to read it is that the important part here is the file name, so test/test_flow.py. So it tells me I've changed this file, and then here the green lines here, these are lines that I have added since I last committed. Right? So I can look through them, and I can just check that this all makes sense, and then I can type in git commit and push. And once you commit it, if you type in git commit, if you commit these changes and you type in git diff again, you'll see that these won't show up anymore. Right? Okay, so git diff works actually really nice if you just changed a few lines of code, and then it works great. If you have many, many changes, then it's sometimes nice to have a graphical user interface. And there's a program called Melt, and it's essentially, it shows you the old file on the left and the new file on the right, and it highlights the differences between the two. Right? And so the equivalent here is you can see these green lines, and essentially you can see that this has been added, and you can kind of scroll up and down, and you can even edit it and so on. Right? So I just think that that's kind of a useful tool that I often use. If you're interested in using that, what you need to do is you need to install Melt, and I think it's available for Windows and Mac maybe also. And then you have to open in your home directory the .gitconfig file and add these two lines here. You just specify that the diff tool should be Melt. And then if you type in git diff tool, then it will open up this comparison editor with all the changes highlighted. Okay? So that's what I use. So I typically use a mix of command line tools. So most of my stuff with Git I do in the command line, except these kind of diffing things that I do in graphical user interface. There are also full graphical user interfaces for Git. So if you don't want to use the command line at all, you can use a graphical user interface for that, and it essentially does the same things. You just have to click a bit more, but they work also really well. And there's the link down here, and that shows you there's various different options that you have. And I don't have experience with them, so I can't give you a specific recommendation. Okay? Tip of the day finished. Okay, let's go back to classes. So the last thing that I want to show you about classes are properties. So what are properties? okay, before I explain why, what they are, I explain you why we want them. Let's say we want to have our point class. Let's look at again our point class. Now the problem is, if the user could just go ahead and really mess up our thing, our point class. For example, you could say p.x equals a string, right? And now suddenly, if the user started using this point in further operations, right, then it would just crash, right? So it would be really nice. So Python doesn't stop you from doing that, right? Because there's nothing like private variables. So the user can just play around, and then things will crash later on. So it would be nice to at least warn the user if he tries to do stuff like that, what he's doing is dangerous. So the first idea on doing that is to implement functions, getter and setter functions. So if you're using C++ or Java, then that's something very familiar. And essentially the idea is we're going to implement a safer version of our point class. And we implement a specific function that the user should call when setting a new x value, right? And so that set function takes in a new x point. And then what we do is, in that setter function, we can check if what the user passed in is actually something sensible, right? So we can check the type of the variable x that the user passed in, and if that's of type float, then we can update. Then we can update the point. Then we can update the variable. And so now I'm actually using a hidden member variable to actually store the x value, right? So that the user doesn't accidentally just play around with it. In a non-public variable. And so if the user passed in something incorrectly, then at least I can warn him. Right? I can print out a warning message. And then, because now this x value is hidden, so then I implement another function that makes it more easy to get that value again. So it's just get x, and then I return self._x. So the way you use that now is you create a new save point, and then when you try to set the point with something that is not a floating point value, then you get a warning, and the original value would not be changed. Yeah, but then if I type in something, say type in 3.4, then it still doesn't work. Let's see. There we go. So then it accepts it. And so, yeah, and then we can get it out again. We can set a value and then get it out again. And yeah, everything works. So the advantage is that with this getter-setter function, we have more control, right? We can do type checking. We can even implement read-only variables. If you don't implement the get method, if you don't implement the set method, then we're essentially implementing a read-only variable. The disadvantage is that the user, what the user has to write in it's quite tedious, and it's not very pretty, right? If you before we just had p.x equals 5, right? So that's, I would say, it's much more readable than to type in point.zx 3.14, right? And when we use this word Pythonic, one often actually means readability. So Python cares a lot about readable code, right? And the point here is that these two lines up here are not very readable. So to solve this problem, Python has the idea of properties. And essentially, you should consider them as being intelligent assignment operators. So they're assignments that can be, that can have more functionality. So, and essentially what's technically happening is that with properties, you can make an assignment call another function. Right? So we can change with the property, we can change an assignment so that it actually calls a set method, which is, and then the set method can implement more intelligence. So in other words, we can change these two lines up here with the set and get methods to something that is equivalent, behaves equivalently, but looks like this down here. So we'd say point.x equals data, you're actually calling the equivalent set method, and if you say data equals point.x, then it actually calls the getX method. So this is what properties allow you to do. So creating properties is simple. So if we go back to our savePoint class, so we've already implemented the setX and the getX method, and now the only change that we need to make to create a property is to attach this x. So what we do is we call the property function, and we tell it which are the get. What is the get method and what is the set method, right? And so here I'm passing in the set and the get method that I've implemented, and then I store that property as a member to the savePoint class. Okay. So now, if I use it, if I create a new savePoint, and I type in point.x equals 2.0, what's going on is that Python will realize this x thing here is this up here. That's actually a property. And what I'm trying to do is in assignments, I'm trying to set x equals 2.0. So the property will call the associated setter method. The setter method I've provided here, it's the setX function. So Python will actually call this function up here. That's what's going on. So this will work, but if I now try to set a string to x, then I will get the warning message. And the same thing works when you try to retrieve the value, right? So if I change this again to 1.4, then here now you're trying to get the value of x, and so again Python checks that's a property. It calls the get method, and get method here also prints out a message. So here's the recommended style when to use all these different techniques. So if you have a variable that that you want the user to be able to read and assign more or less arbitrary values, then you just use a normal class member variable. There's no need to make it more complex than it can be. You can use properties if you want to have certain variables to have restricted access, or some kind of type checking, right? There you can use a property with an underlying non-public class attribute. So that was kind of the hidden _x variable that actually stores the values, and then we use the get and setter methods in the property to make it accessible. Yeah.
Why is it meant to use double underscore then for the
for the double underscore for the x variable? I guess you could do that. Yeah. I guess it depends a little bit how much you want to hide it. Yeah. Also, properties are really useful if you want to make an assignment that also does certain side things at the same time. Let's say an assignment should print out something to screen, or maybe if you want to assign, you also want to write something out to file, right? So if you want to implement things like that, then also properties are the way to go. And so maybe just as a warning, so using these get set functions explicitly is typically not a good idea. So if you implement get set methods, then also make it a property so that it becomes more Pythonically available. Good. So just a few words about scopes. So scope, this word scope just means if you create a variable in Python, how long does it live, right? How long is it accessible? And essentially there are two different distinctions. There's a local scope. So these are variables, but also function arguments that are declared inside a function. And so anything that you declare inside a function or that comes in as an argument to a function has a local scope, which means that once the function is finished, these variables are lost, right? They won't be accessible anymore. And then there's the global scope. So these are variables that are defined outside a function, and they can be accessed and changed by the function inside, but they are also still accessible after the function has finished. Clear? Let's have some experiments. So here's a code example. What do you think the output will be? Let's just wait for 5 more seconds. Okay.
When you call f, it will print, but when you call the triple x variable, it will say it's not declared.
Okay. Any other suggestions? Everyone agrees? So let's see what happens. Yeah, that's exactly right. So we see, so f is being called, right? Then we create a local variable, triple x, then we print its value, but then we're trying to access it. So then the function is finished, so we go outside again. But because x was a local variable, it will not be accessible anymore after the function is finished. So at this point here, when we're trying to access the triple x variable down here, the program just crashes and says the name triple x is not defined. Yeah, but we did see this one here, just like you said. Okay, next example. Okay, one idea?
First, the function is going to print 1, and after you change it, it's going to print 2.
Okay, so we have one vote for first 1 and then 2. Any other ideas? Okay, everyone seems to agree. Let's see what happens. That's exactly right. Good. Okay, next one. Yeah?
It's going to be this with 2 entries, hello and world.
Okay, so we have someone saying it's going to be a list with 2 entries, hello and world. Does anyone think it crashes? No? Any other suggestions? Maybe it's just too easy. Very good. Okay. That's it. Okay, but did you get the ideas of kind of local and global scoping? To some extent, maybe? Is it anyone not clear why this works? Yeah?
For each indent area, you have its own scope. So when you write a data and world, it will first look in the immediate function declaration if there's a variable called a, and then it will look inside f, and if it can't find there, then it will look globally, and there's a variable called a.
Yeah, so that's actually a very good point. So let's change it. So what do you think happens now? Hello or hello world? Just hello. Okay. Exactly. And so the reason now is because this append here, so we're calling G up here, right? G appends something, it appends the word world to the variable A, but the variable A now is the closest variable A that is in the scope is this one here, but this variable A here only lives within the scope of the function. So as soon as we leave the function again, we are back to the variable A that was defined up here. And that's what's being printed out on here. So that was a very good... Okay. It's just something to be aware. So sometimes you might be, you write a program and you're kind of a little bit maybe surprised of the behavior, but it might be because of the scoping. Modules. So you've used modules already a little bit in the exercises. I just want to actually explain how they work. So a Python module it's essentially just a file that consists of Python code. And so a module or that file, it can contain functions, it can contain classes, and it can contain variables, but it can also contain just runnable code. So essentially, a Python module is really just a Python file. Or any Python file is also a module, if you want to take. So why do we use modules? And what are they good for? So you want to use modules mostly to organize your program logically. So for example, maybe you start writing your script and it becomes more and more complex, and you realize you can split code into several files with specific functionality to make it easier maintainable. You can also group related code into a module. Right? So maybe you have code that does all kind of mathematical functions, and you just want to have them all grouped together into one file or one module. It's also useful to share code between scripts. Right? So in case you want to have, maybe you're doing some maybe some code to download some files from the internet, right? And you want to actually use that code through multiple projects. So one idea would be to make a module out of it and then use the functions in that module for all the scripts that use it. And then finally, you can actually publish modules on the web so that other people can use it. And you've done this, you've used other people's modules already some people use NumPy, and even though these are packages, but still modules inside packages. So you've actually used already this feature. So how do we use modules? So the general syntax is the important keyword is the import statement. So you have import, and then it's the module name. And so in this case, sys is kind of a system-wide module that comes with Python. So in this case, we're just loading in the sys module. And then we can, so remember, modules contain functions, variables, and so on and so forth. And so this particular module here contains a variable called argv, which is a list. So here I'm accessing the module's variable argv and access its first entry. That's what's going on. So there's another syntax that you can use. You can write from sys import argv. So after you've done this, you have the argv variable directly accessible in the code. So then you can use, you don't need, so up here we had to write module name dot variable name. If you use the from sys import argv syntax, then you can just use the variable argv just as if it was a local variable. Finally, you can write from sys import star. That actually imports everything that's contained in that module. All variables, all functions, and so on will be immediately in the namespace scope of your program. And so obviously, part of the star is also argv. So this will still work. I can still write float argv1. The problem now is that you also have suddenly loads of variables in your namespace that you might not be aware of because we've imported everything. So in particular, if I now create a new variable, let's say I start creating a new variable flex and just set it to 0, an empty string. Incidentally, what I've done is flex was already imported from the sys module. So what I've done is now I changed. I've overwritten a variable that was imported from the sys module. Right? So one has to be really careful when using the star, and it's typically not recommended. It's much better to explicitly state which variables you're importing.
Question.
Yeah.
What's the difference between writing import sys and from sys import star?
Right. So if you look at the essentially when you write import sys, then you have in the program below you have sys as a variable, and then you can write sys.argv. Right. So if you write from sys import argv, then in your program you have argv as a variable available, right? And then you can just write argv. You don't need to have the sys dot here anymore. Right? So that's really the only difference. Yeah. Wait. Yeah, and then finally you can import. You can actually rename variables. So sometimes it's a problem. Maybe you have two modules that actually have the same variable name that you want to import, right? So there's a name conflict. And so in these cases, you can give the variables that you're importing, you can give them your own name. So you can write from sys import argv SA. And if you do that, then now this argv variable will be available as an alias under the name A. So now you can write float A of 1. Okay? Okay, so that's how you use Python modules. Now, how do you actually create your own ones? And it's really easy. What you need to do is you take all the functions and all the variables that you want to have as part of the module and store it in a file, in a Python file. So for example, mymod.py. And then you put this mymod.py in a directory where Python can find it. And I'll show you how to do that in a second. And that's it. And that's how, now you've created a module. And now you can start using it. And so the way you use it is, for example, import mymod, or if, let's say, this Python file contains a variable m. Oh, sorry, you can write import mymod as m. You can import everything that is contained in this module variable, or you can import some functions. Maybe you define a special function in your module, so you can import that. Okay, so what I'm saying here is that essentially, if you want to create a module, let's say you have a function in your script and you want to make it into a module, just copy that out that function, store it in its own file, in its own Python file, store it in a directory where it is accessible. For example, the same directory where the script is. That always works. And then you can just write import. And then, so here the important part is the name that you use here is the file name that you've chosen without the .py. Yeah. Is that clear? Good. So there's a valid question: how does Python find your module? There's a few different. There's a kind of few different official module directories where Python looks for modules when you're trying to import it. The first one is some kind of system-wide directories, for example, userlib Python side packages, where this is where all kind of the system-wide packages and modules are installed. Then there's the local environment variable Python path that Python checks. It looks at all the directories that you've defined in Python path and checks if your module is in there. And finally, it also checks your current directory path. In fact, I think it goes the other way around. It first checks your current working. If you have kind of the same with the same module name in multiple places, it first checks your current working directory. So I often have modules in the same directory where I have the scripts in, at least for a starting point. So this Python path directory that essentially contains a list of search directories where Python looks for modules. And you can check which ones this is on your system by typing in echo Python path, and then you get a colon separated list of paths. Right? So here I've changed my system's Python paths because I have some modules in home Simon source CBC block, and I have some more modules in home Simon source OptiCell. Right? And I want to make sure that Python finds these modules, so that's why I've changed this environment variable. So how do you actually change it? So these are bash commands here, echo and export. So in your bash, you can type in export Python path equal, and then you can add a new directory. You can specify the directory and where it should look like. And then I also use colon and just append the old Python path that I had previously. So I just extend the Python path with a new directory. So in principle, what you could do is you could have kind of one directory where you store a bunch of modules, and then add it to your Python path. And then wherever you have your scripts, you can import these modules, and Python will find them. There's one useful thing that for modules. It's normally when you import a module, Python actually executes all the lines that you've got in there. So if you have a function, then it will if you define a function, then the function will be defined. But if you also just have some print statements in there, kind of as normal code, then when you import the module, Python will actually execute these print statements. I personally often use a module as a standalone. So in the module, I define a bunch of functions, but I also want to make the module self-executable. So if I just type in Python module name.py, I actually wanted to run some stuff and maybe test some of the functions I've defined in there. And so in order to prevent that these tests are also being executed when I import that module, what I do is I add this if statement in here. So there's no need to, really the important part is here, this if statement only evaluates to true if you run Python module name.py, and it evaluates to false if you import that module name. So this piece of code is only being executed if you run the module as a Python program, but not if you use it as a module. And so I use exactly that often to just run some tests and make basically a module testable directly, or just some user examples on how the module can be used. Yeah, there's packages. I'm actually not sure if I should. So a package is essentially just a collection of modules that you can have. So many of these NumPy, for example, or many of the libraries that we will use, they don't just consist of one module, but they consist of an entire collection of modules, which is then called package. Yeah, and so the way this works is that you have a package is just basically a directory. And in the directory, you can have module files. But also each directory and subdirectory of that must have the special __init __ file. And it can be empty, but the pure existence of that makes that directory a package. Okay, so I show you an example. Let's say you suddenly started making more and more modules, but they kind of have thematically the same purpose. So you want to collect multiple modules into one package. And then what you do is you create a directory, in case it's still called mymod. And that directory calls a file init underscore init underscore. And then in there I have a subdirectory called numerics, again with init underscore init. In there I have a subdirectory called PDE, again with this init file. And then finally in there I have my Python file grids.py that defines some functions. Right? And so obviously you could now start adding more Python modules in these subdirectories. But it allows you to kind of structure more complicated projects into subdirectories. So this is now called a package. So now how do you access this FDM grids function that lives in this quite complicated package? Well, essentially, using exactly the same syntax, you're just following down the directory tree now. Right? So now when you want to import this, you write from mymod.numerics, right? So this just means in the numerics folder, .pde, so now we're going into the PDE subfolder, .grids, right? So grids now is a normal module, it's a normal Python file, and then in that we can write import FDM grids. So now we followed all the directory structure all the way down to a module, and then we imported the function of that module. And then we can use it just like any normal function. And so you might never create such a complicated project, but when you use other people's projects, so for example NumPy, it's very common that you have kind of module name and then subdirectory, and finally you're in the module where you add the function that you're looking for. And so just for you to be aware that this is how it's structured. Okay. Documentation. So that's something really important. And I've mentioned it before, but I just want to explicitly say it again. So whenever you create a function or a module or a class in Python, when you have the first line in the class definition can be a string, and that string will be interpreted as a documentation string of that function, class, or module. And these are called docstrings, and they're very, very good practice. So whenever you write a function that is maybe not just used internally, but used by users, it's a very good idea to add a docstring that explains what the purpose of that function is. So I've got an example here. So this is, let's say, a Python module that I've written, and so here I want to use that as a module. So I use the first string. So this is a multi-line string. I use that string to just describe what that module is all about. So it's a collection of mathematical functions. And then in that module, I also define a function. And again, in that function, the first line is a string. And there's different opinions now what a good docstring should look like. But a good starting point is that in the first line, you just say what that function does. So in this case, it calculates the sign of a number and returns the result. So it's a short summary of what the function does. And then you can have a new line, and just below, if it's more complicated, you can specify in more detail which parameters this function takes, which types they are, and so on and so forth. So if you're interested in kind of a guideline in how to write docstrings in more detail, you can follow this link. So there's a Google docstring guideline that works really well. So, okay, so there's obviously documentation of the code itself, and you read the source code. But another reason why it's a good idea to write these docstrings is because your editor will actually facilitate you to get these docstrings out. For example, in IPython notebook, when I defined these, let me just show that I executed this. So I defined this min_sin function here, and I added a docstring. And now in IPython notebook, I can just write min_sin question mark, and then you'll see this window popping up down here, and you'll see that the docstring is immediately available. Right? So in particular, if you have this function stored somewhere in a module and you're not entirely sure anymore what it is, then it's really useful to have these docstrings easily available. You can also have them, you can actually get the docstring as a string object again with a magic __ doc attribute here. So then you can print it out, for example. Okay, shall we, I wanted to talk about testing, but yeah, it's free to, maybe we just postpone it to next week. Are there any questions? No? Okay, then have fun with the exercise and see you next week.